So you should have a good practice so that you can write the equations quite quickly. Okay, the energy E of the bound states of a particle of mass m, okay, in the one-dimensional potential. Let me draw the potential like this. My potential is infinite here, okay. It is some minus V naught from 0 to A. Can I say like this? Fine. It is some minus V naught A here. And again, it is 0 for x greater than A, okay. And he's asking, I'll say this is minus V naught here, okay. He's asking what is that bound state, okay. Bound state means, I mean, if energy greater than 0, it can come, hit, and it can go back. It is scattering state, okay. Bound state must be, energy must be less than 0, greater than minimum value of the potential. Energy must exceed minimum value of the potential. So that's the theorem, okay. Fine. So this is energy less than 0, okay. Which of the following equations are followed like that, okay. Transcendental equation. I think some sentences are missing in the question, okay. So then you start writing wave function is 0 here, that we know, okay, in this region, okay. Fine. Here in this region, can I write wave function quite directly? I mean, this is classically forbidden region, am I right? In the classically forbidden region, I mean, your solutions are what is that, a e power kappa x plus b e power minus kappa x, am I right? Minus kappa x. But among these two, b power minus kappa x should survive, because this region means it contains x tends to infinity. As x tends to infinity, your wave, I mean, bound state wave functions must be normalizable. Okay, fine. So that's why let us pick this one. Okay, fine. This kind of solution. Okay, so that, I mean, that you should able to write quickly, not writing Schrodinger equation again. Okay, fine. In this region, it is sinusoidal. Okay, don't write e power I theta format. You write sine and cosine, both sine and cosine. Let us write like this. Okay, I'll write in this region. Okay, fine. My solution is a sine kx plus b cosine of kx. Fine. Where k equal to root of 2m, classically allowed region. Am I right? 2m e minus e minus v. I'll write like this. Later I'll substitute v as minus v naught. Okay, e minus v, okay, divided by h bar. Am I right? So in this region, okay, your solution a b c e power minus kappa x, okay, where kappa is equal to, because in this region potential is higher, energy is lower, okay, so 2m v minus e divided by h bar. Am I right? Classically forbidden region. Now look at here. Here only I will do something because it's an exam question. Am I right? We can't spend time to do the derivation. Here only, look at here. In this wave function, this cosine will not allow wave function to be 0 at x equal to 0. Wave function continuity must always follow, isn't it? So that's why at x equal to 0, this wave function must be 0. Am I right? I mean, later we will care about continuity at x equal to a. That's a different story. Okay, this one continuity with this one. Okay, but if you want to talk about continuity of this a sine kx plus b cos kx with a wave function when x less than 0. Okay, so cosine should not be there. Why? Cosine of 0 is not 0. Am I right? Speak up. Because wave function is 0 before this one. Okay, that continuity of the wave function demands that. Okay, so this should not be there. Fine. For that we make b equal to 0. Okay, or here also if you write c e power kappa x, okay, so plus d e power plus kappa x, okay, exponentially decaying. I mean, these are the solution, general solution. Okay, but in this region this should not be there. Am I right? This should not be there. Okay, that you should quickly judge actually. So that's why. Okay, so in the, I mean, your wave function will be like this. Okay, what is this one? This is 0. Okay, when x is less than 0. Okay, fine. It is a sine kx when x is between 0 to a. Okay, so then it is c e power minus kappa x when x is greater than a. You should quickly write this one. Where k and kappa are given like this. Okay, later you need to substitute k and kappa. Look at here, he gave everything in terms of energy, potential, and all. Okay, I just wrote V here. V is nothing but minus V naught. Okay. Later you need to substitute V equal to minus V naught. Okay. Fine. Now what you do? Here continuity of the wave function is already taken care. Am I right? At x equal to 0, avoiding cosine function. Okay. So you have to apply continuity of the wave function and its derivative at x equal to a. Can you see this one? So a sine ka, I mean continuity of the wave function. So at x equal to a, okay, that's equal to c e power minus kappa a. Fine, one equation. Okay, so then I need derivative also, isn't it? I need derivative also. I'll just take the derivative here. Okay, d psi by dx. What is this one? A k cosine of kx minus c kappa e power minus kappa x. Is that right? Derivative continuity at x equal to a. I'm applying quite directly. Okay, fine. So that's equal to a k. Okay, cosine of ka. Okay, that's equal to minus c kappa e power minus kappa a. Fine. Derivative continuity. Okay, I'll say this is equation 1. Okay, this is equation 2. You just divide them. Okay, check the option first. Okay, cosine, tan, these things are there. Am I right? And he took square, so that root can be removed here. Okay, fine. Can you take the I'll say the second equation divided by first equation. Okay, because kappa will remain in the numerator. Okay, second equation divided by first equation. Can you write down? First equation was a sine ka, that's equal to c e power minus kappa a. Is that right? This was first equation. I'll divide second equation by first equation. Okay, then sorry, second this one by this one. Okay, so k cosine of k cot ka. Okay, that's equal to what is here? Minus kappa minus kappa. Minus kappa. Okay, so now you just see the option, keep seeing the option and square it. Okay, that's better. Okay, fine. So that is, if I square it, okay, k square cot square ka. Okay, that's equal to kappa square. What is this one? K square. So I mean I should not have kept it like this. Am I right? K here, this is simply, okay, root of minus 2m e divided by h bar. Am I right? This kappa. Okay, it's directly like this. Okay, so but here v is equal to minus v naught. V equal to minus v naught in this equation. Okay, fine. Check this out. Okay, so now that this is 2m e minus v divided by h bar square cot square ka. What is this one? That's equal to minus 2m e by h bar square. Okay, fine. So now that cot square k, what is k? E plus v naught will happen. Am I right? E plus v naught. Okay, so cot square ka, that's equal to minus e divided by e plus v naught. Right? This one, e, v is minus v naught. Okay, fine. So cot square, I think he might have substituted that k also, right? Cot square a times k. Okay, what is k? Root of 2m. Okay, e plus v naught. Am I right? E minus v, but v is minus v naught. Okay, divided by h bar, that's equal to minus e divided by e plus v naught. Okay, fine. Minus e divided by e plus. You don't have to worry. Okay, energy is negative. That's why this negative sign won't sustain there. Okay, fine. So check that out. Okay, compare with the answer key later. Okay, fine. So that's what they are expecting. At least you should able to write this. That's why we did the whole derivation. Am I right? I could have mentioned the final result of that Finite square well. Okay, so this should be done. This is a solved problem in uh, Jetili outside. Okay, and you can see here only cot functions are coming here. Am I right? In our usual Finite square well, both cot and so tan functions are coming. Okay, in our transcendental equation, and we had many bound states over there. Fine. Now, one more thing that you should understand here is, okay, you don't have you don't have tan function. Am I right? Fine. Do you can you recall? This is to solve next problem actually. Okay. Since you don't have tan function, you used to have tan cot like this. Can you recall? Hmm? If you recall your Finite square well one. Okay. So now only cot exists actually. Okay, so that's why your first bound state, okay, fine, that will have quite higher, and this will not be there actually, this tan curve will not be there. Okay, fine. So then when you start drawing one more equation, that circle equation, okay, when you start finding the intersection, okay, so your ground state, okay, for this well, okay, that is slightly higher than the ground state of our earlier one. Earlier one, this curve was there actually. Can you recall? This curve was there, and this intersection point was a ground state actually. Okay, but now for the same width and all, same width, same depth. Okay, now your first curve is this one actually. Okay, cot curve. Okay, that's why your ground state have increased. Okay, so do you remember this? This horizontal was Ka or something. Okay, that K will decide energy. Hmm. So that's why ground state energy, okay, of this one, okay, it is higher than ground state energy of usual Finite square well, where there is no infinity one side. Fine, that logic you need to grab, because you got cot function only. Okay, no tan function. Okay, this were tan function actually. Okay, this is pi by 2, pi, like that. Okay, these functions are not there. Okay, these were your tan function. Okay, only this cot function exists. Okay, so that's why uh, the first intersection point of first curve, that is our ground state. Am I right? Fine. So that ground state will be usually having higher energy than the ground state of our usual Finite square well. Okay, that you should get. Okay, or there is one more jugaad way here. So you had a usual Finite square well, no infinity here. You started raising this wall to infinity. So it was in the ground state of our old Finite square well. So there was no infinity here. Okay, fine. Now you slowly rise the wall to infinity. Then this energy should also rise actually, because you need to do some work in order to rise this potential to infinity. Okay, you can use that work energy idea, okay, to say that ground state energy will also increase. Okay, so because we need this one for one more problem. You got my logic? So grab this idea. For one dimensional potential well A, B, C, as shown in the figure, let EA, EB, and EC are the ground state energies, okay, of the particle respectively. Okay, the correct ordering of the energies. One is Finite square well, but not same height in the both side. Okay, but another one is just whatever we solved. Okay, one side infinity, other one is particle in infinite square well. Which ground state will have higher energy? Which ground state will have least energy? Has higher energy. Then B, then A. Okay, EC is highest, that's what you're saying. Then EB, then EA. What is the logic? So what? You can again apply work energy kind of idea. You started with this one, it was in its ground state, Finite square well. You started with this one. You rise one of the wall to infinity. You needed to do the work. Okay, that's why ground state energy slightly increase. Now you need to raise one more wall to infinity. Again, ground state energy will rise. Okay, or so other than this Jugard logic, okay, there is one more way. From finite square well, we went to infinite square well. Can you recall? Hmm? So I have taken my finite square well, that symmetric, antisymmetric states and all. Can you recall this one? This was, I think, pi by 2, pi, 3 pi by 2 and all. Okay, tan curve, cot curve and all. Okay, can you recall? I think this was your Ka, as I recall. Okay, this was our Ka. Okay, fine. This was our kappa A or something. I don't exactly remember what we did over there. Okay, but our circle, okay, it used to cut like this. Am I right? Circle of radius r or something. Now that r contain, okay, a root of v naught, isn't it? Root of v naught, height of the well. Now if you make v naught to infinity, okay, if you make it infinite square, well, what will happen? This will become a circle of infinite radius. When that become very big circle, okay, again I need to increase here also. Okay, fine. When that become like this, okay, now this is going to cut our symmetric and antisymmetric state, okay, exactly at pi by 2, pi, 3 pi by 2 and all. Okay, that means your Ka will be, so what is that? N pi by 2. Ka will be n pi by 2. Okay, what is K? Root of 2m e by h bar. What was the Ka or Ka by 2? Ka by 2, I think. Check this out. If width of the well is A, this was K and kappa A by 2 actually. Okay, that I don't quickly recall, but I have some logic here. Okay, find the root. This is Ka by 2. Am I right? Ka is equal to n phi. What is this condition? This was 1D box condition. Kappa A by 2, A by 2. Okay, kappa A by 2 here, Ka by 2 here. Okay, fine. Now what I am saying is this is our exactly 1D box condition. Am I right? This is root of 2m e by h bar, that's equal to n phi. You will get En is equal to n square pi square h bar square by, okay, 2m a square. Okay, width of the well is width equal to a. Okay, that is the idea that I have taken. Okay, so that's why you should always now look at here. Okay, when this was a smaller circle, okay, one of our transcendental equation, your ground state was somewhere here. Am I right? I mean, for some finite value of v naught, okay, your ground state was somewhere here, isn't it? When that r tends to infinity, when v naught tends to infinity, when that r tends to infinity, this point moved to this one. That means Ka value became higher, energy value became higher. Okay, that is another logic. I think I did this one, okay, during that topic. Okay, so that's why I can always compare this one and this one. Even though we didn't practice this middle one, okay, you can always compare these two, isn't it? So this one will have lower energy, this one will have slightly higher energy. Okay, so with that one also I think you can eliminate option. Okay, check that out. Okay, and this comes in between. Somehow argue that this comes in between. Or the Jugard logic, like you were in the ground state, you were in finite square well, you started raising the wall. Okay, I mean some energy conservation or something, ground state also slightly increase. Okay, you can do that.